Hi, my name is Chris Jurgensen, and I'm an associate professor of biochemistry at Delta State University. I put together the educational content for this module on protein crystallography. The figure you're looking at right now is a picture of a protein crystal I worked on many years ago. It's a picture of what it looked like, kind of a rod shape. And after that, there's an arrow that shows what kind of looks like a mess. It's just a bunch of what appears to be some secondary structures, and the protein was built by a program called Solve and Resolve, which is part of the AutoSolve program we're going to be talking about that's used to solve protein crystal structure from what's called anomalous data. And as you can see, it started off with some bits and pieces, which really wasn't maybe all that helpful initially, but this was actually a pretty good picture of the protein itself, gave me a starting point to start building. And then after a few weeks of working on this in front of the computer, I had built a nice structure. And then, of course, we finally published that structure. It's a 16 synthase enzyme. So what we'll be doing for this module, the purpose overall of the module is to kind of give a crash course in how to use protein crystallography and how to use X-ray data to solve protein structures. There's a pretty big learning curve. Worked in research for 10 years before becoming a professor, learning how to do these things. And of course, the field evolves a lot. So a lot of what this is going to be will be pretty fundamental things as to how crystallography works. So I'll talk about that a little bit as far as how the modules are set up and what to think about in terms of how we're going about teaching this. So the way that this Jupyter notebook is set up, there's a README and there's three submodules that are specifically associated with crystallography, 1 through 3. And the modules have to do with different aspects of crystallography. So what's nice about this is that learning how to use crystallography is very difficult if you're not set up in a lab that's equipped with the right kind of computers and software and also know-how. Even having access to the software may not help if you don't know how to use it. And this has been one of the challenges over the years that I've often faced is dealing with computers that maybe don't have scripts that run properly or beep continually or software that's not stable. And it can be very frustrating because you wind up spending more time trying to get the software to work than actually playing with your data and looking at structures and building things. So what's nice about this notebook is that it'll have all of the software you need already integrated into it. So that gets over some of the more difficult hurdles that are associated with it. So the learning curve when it comes to crystallography is very high. And certainly by the time you've gone through this module, you'll in no ways be an expert, but you'll have had a chance to experience working with data and solving structures and working with some of the key programs that are used for that. And then also, of course, translate that into other projects as well. So if you collect data, you should have some idea on how to deal with it. Also, when looking at structures downloaded from the PDB, you'll have familiarity with the software that's used to visualize them. And that's very helpful too. It's something you can do all the time, is check and work with other people have done. And you'll have a better handle on how to look at things like electron density maps, what you're actually seeing. When teaching students or people who are new to the concept of proteins, it's hard enough for them to understand the two-dimensional version of things like active sites and residues that are involved in, say, hydrogen bonding or Coulombic interactions. But then showing them a picture in a molecular graphics program that's a 3D version of that same active site, often people get lost. And so it's something that you can get better at simply by practicing, but it definitely does take some time. So the purpose of these modules is to do an introduction in crystallography, which is really what the purpose of this first submodule is. You can go through and read it. I'll have a separate video sort of describing each of these things. But I like the idea of putting together some concepts that aren't the sort of things you typically see in a textbook. If you read biochemistry textbooks, they're certainly going to cover some of the same ideas. But one of the things that I really like to focus on when I'm teaching this and trying to understand new structures myself is what's actually going on, because we have the luxury now with crystallography and also with cryo-EM and mRNA methods, we can look at interactions between atoms specifically. So we don't have to guess what an enzyme is doing, like in this figure I'm showing here, the Pac-Man model. We don't have to guess. We can see exactly what it's doing. And if we can't see exactly what it's doing, we still can get a pretty good idea. There's another model that's being developed on ligand docking. So if you have a protein structure and you know that a ligand binds to it, you can also model that as well. But you do need a protein structure first. So some of the introductory concepts are like, what is exactly the problem? What are we dealing with? What can we learn from this? And yes, of course, I get into a discussion as well of the concepts of AlphaFold. AlphaFold is very useful, but AlphaFold can't do everything. AlphaFold is not going to tell you if another protein binds to your protein you don't know about. It's not going to tell you if a small molecule will bind to the active site. Those are separate questions. It's immensely helpful because now we can use known structures to solve structures from X-ray data. So we'll talk about that in the molecular replacement module, but it's still not something that has an answer to everything. And like pretty much everything with AI, it's perfectly fine to use. It's very helpful, but you shouldn't use what it gives you whole cloth that it puts out. You have to look at that and interpret it, and make sure it makes sense. And I give an example of where AlphaFold did a really good job predicting something and then not a good job predicting something else. This is a small protein that is actually part of that structure that I showed in the beginning of this video. And so there's some considerations we have to think about in terms of how to crystallize a protein. And of course, when you do that, there's an art to it. Many people have thought of it as being an art. You've seen two people or examples of two graduate students or two postdocs working on a research project. They're both trying to crystallize something or have in the past, and one person is successful and one isn't. They're using the same screening kits, probably the same conditions, but one person just has better luck at crystallizing things than another. It's kind of an art, but it is also related to technique and skill and just being patient. And sometimes you just have to keep trying things until something works. Some proteins won't crystallize at all either, which is immensely frustrating, but at least that is often not the case. The smaller proteins that are soluble that can be crystallized. And once the crystal is obtained, then the next issue is data collection. And we'll be talking about examples where data collection, of course, works really well. Sometimes crystals look great and don't diffract at all. But in these examples, where we're looking at actual structures, they do. There's some discussion of theory. Of course, the beauty of this is that you can take a diffraction pattern that looks like this circle here. And of course, that alone isn't enough. You need several of them. But these diffraction patterns don't really look anything like a protein. But of course, that's because they exist in what's called phase space, and a Fourier transform can convert them into an actual electron density. That does require solving the so-called data problem, which we'll talk about. But it's remarkable that the data can be collected and converted into a structure that teaches us something about the actual atomic coordinates of an entire enzyme that can be quite large. It's a very useful technique, and with advances in synchrotron data collection and detectors, data sets can be collected in minutes. The first data set I ever collected many years ago took 6 hours. Was at a relatively weak beam line, but it produced a great structure that I got a lot of mileage out of. And so for a lot of other people too, this is something that the data collection part really is, well, it's fast, which is great for high throughput. Really, the time-consuming part is taking that data and turning it into an actual structure, model building and refinement. So the way that this module is set up is an introduction, and then the next submodule is going to be a discussion on solving structures, and then the final submodule is dealing with COOT. So the submodule uploading or the third submodule will be done using COOT, which is a molecular graphics program that we use for building models. And COOT is a pretty handy to use because of the fact that it's relatively straightforward. Here we go. So it's determining structures using Phoenix. Phoenix is a program that's freely available and is basically a user interface that has a lot of programs in it that pertain to structure solutions by things like anomalous scattering and molecular replacement and also refinement. And it's very handy. It's all in one spot. I like it because, again, everything works pretty well. So the modules are set up and there's screenshots of different aspects of each of these processes. We have data from the protein data bank that's been used to solve the structures and also kind of some explanation of what is in the data files that we've used. And then an output and what it looks like in COOT, and then how to interpret the data. And both using SAD phasing as well as with molecular replacement. There's some strategies we use. So trying to find a structural analog is important, so we can use that as a search model. And of course, if that doesn't work, if there doesn't exist one of a real structure, you can always try AlphaFold. AlphaFold can produce a lot of useful structures as well. So that's another example of what we've been learning. And then again, finally at the end, there's a submodule dealing with COOT. COOT is the crystallographic object-oriented toolkit. Very, very useful molecular graphics program for building models. This is a screenshot of it, kind of showing where some of the electron density is, or the backbone atoms and residues that need to be built into this data. So we'll be using a couple data sets that are pretty easy to interpret. Now, if you were actually doing crystallography and collected a data set that was 4 or 5 angstroms, it will be very challenging to build in some of the structure. This is a data set that's closer to 1 angstrom. So it looks like all of the atoms are shrink wrapped by this electron density. And so if you have the luxury of working with something like that, it's great, it's pretty easy. But even still, there are going to be some times where Cube may insert the residue incorrectly as you're building in some of your structure. So you have to know what it is to expect. You have to have an idea of where the backbone atoms are, and where the side chains are, and what direction they're pointing. And even something as subtle as a histidine residue has to be oriented properly so that the nitrogen atom that can accept or donate a hydrogen bond and accept a hydrogen bond, that those nitrogens are positioned properly, because sometimes they aren't. So these are things to look for as you go through. So what we'll be doing is just learning some of the tricks that are involved in doing crystallography. There's some theory in here explaining more or less how it works. And by the end of this, you should have a handle at least to get started doing crystallography in your own lab. That's the goal of, ultimately the goal of the modules, so that if you don't have a lot of experience doing this, you can gain some quickly, and then also have access to software that will work right away. And from there, between talking to other scientists, and certainly beamline scientists can be a huge help when it comes to understanding how to deal with some of these projects. Getting over the initial hump of getting started should be taken care of, and should help you become a lot more productive in the field of protein crystallography.